real exam questions. This is question 64, a slab design with equal deflection and yield lines. Determine the bending moment at the center of a square slab with side L, simply supported on the four sides and loaded by uniform distributed load Q. You do it by using yield lines, and you do it again by using the method of equal deflection. Why is the bending moment determined by the method of yield lines so different from the bending moment determined by the method of equal deflection? And the second question, prove that the bearing capacity of a square slab in a plastic calculation is approximately 1.5 times greater than in a good design in an elastic calculation with equal reinforcement. Let's start equal deflection. We have four sides simply supported slab, so that means that's a type 1 slab. So A is equal to B is equal to L. Equal deflection at the center of the spans is then given by WA and WB, but it's simply supported, so this coefficient is 5. And the formula for equal deflection gives you the load in direction of A is equal to this formula. WA over WB is 1, and A is also equal to B, so we get 1/2, which is logic. So the bending moment is then QA L squared over 8, and QA is Q over 2, so we have QL squared over 16. That's for the equal deflection. Now let's have a look at the yield lines. The supports are axis of rotation. It's four sides simply supported, type 1 slab with the size is equal to L. The virtual work done by the external forces is equal to the virtual work done by the internal forces. It means E must be equal to D. You can write it in this manner. And when you look at the virtual work done by external forces, we got in this triangle the length L times L over 2 divided by 2, the surface of the triangle, times Q, the load, and the mean deflection is delta over 3. And this must be equal by the virtual work done by internal forces, which is this yield line M projected to the axis, so it's M times L, and the angle of rotation is delta divided by L over 2, and we got that 4 times. So in this formula, I put only this line and then added this line to it. So it's the same. So you could take this as one piece. The bending moment from this equation is then equal to QL squared over 24. So yield lines is an upper bound method with a plastic dynamic design. It's dynamic and it's a plastic design. And the bending moment is then given by QL squared over 24. The equal deflection method is a lower bound method with an elastic design and a static design. And the maximum bending moment is QL squared over 16. So it's the same slab loaded with the same load, but you have a different maximum bending moment. And this is because yield lines is upper bound and equal deflection is lower bound, or yield line is plastic analysis and equal deflection is an elastic analysis. Now let's look at equal deflection. The bending moment, from the bending moment of equal deflection, we calculate the needed reinforcement, and the lever arm, the 0.89D, we can write it because in the question was set by optimum use of the materials in an optimum design. So we know this is 0.892. We also, this is for the resisting bending moment, the bending moment resisted by the reinforcement. And for the acting or soliciting acting bending moment, for equal deflection is, of course, we just calculated QL squared over 16. So the the acting bending moment must be equal to the resisting bending moment. So those two equal to each other. We obtain this. And from there, we can calculate the load that can be taken by the method of equal deflection. And it is equal to this formula. Now let's look at yield lines. The bending moment, the resisting bending moment in yield lines is per definition 0.9 times d FYD and the reinforcement. The acting bending moment is equal to QL squared over 24. So acting equals resistance. So we take those two are equal, and we get for the load that can be taken by yield lines is equal to this formula. Now, if you compare those two, and it was said that the reinforcement was the same in both slabs, the reinforcement was the same, then we see that the ratio of the bearing capacity of the two slabs is equal to 1.52, or let's say 1.5. So for a square slab, if you calculate it with yield lines, you have 1.5 times more capacity than the method of equal deflection.